So, welcome back student to the next class of complex analysis. So, in the last class we learned about the Taylor series, and if a function, if I want to make a Taylor series expansion, it will essentially be a power series if it is analytic in a region some d, and in that region if z0 is there, I can expand this function in terms of this power series with ak having the form this. So, I have already written the expression that we find in our last class, that fz is given to this, and we were asked to expand this particular function in terms of Taylor series around the point z0 is equal to I. And I did the calculation and my result was something like this. So, I just write it because I need to show more about that, and we also find out what is the radius of convergence of that particular series, and we find the radius of convergence is √2. So, if I make a circle of that particular point I, circle around that particular point I with a radius √2, then that is the region of convergence of this particular series. At that point also I need to show you one thing that I just mentioned last class, that is Maclaurin series. So, Maclaurin series is a special form of Fourier series when z0 is equal to 0. That is the condition I need to put. So, here what should be the Maclaurin series? The Maclaurin series is simply z to the power k divided by 1 or just z to the power k. This is the standard result where k running from 0 to infinity, k running from 0 to infinity, and this is the standard result that we have already, we know, there is no, I mean, so this series is already known to us, and if I expand this series in terms of Taylor series at that particular point, it looks something like this, where I am doing the expansion at z0 equal to 1 I point. But here in the Maclaurin series I am doing the same thing, but my z0 point is not I, rather 0. So, if I put that, then 1 by z, this quantity, if I expand, it will be something like this, k 0 to infinity z to the power k by 1. Now, if I expand this, it will be just 1 z, z squared, z cube and so on. This series, it is already known that I mentioned. In a similar way, you can now, if I do this function, say e to the power z, if I expand in Taylor series at z equal to 0 point, it will be just 1 plus z square by factorial 2 and so on. So, this is an expression of e to the expansion of e to the power z, which is nothing but the Taylor series at z equal to 0 point. Also, the same way I can expand sine of z, which is z minus z cube divided by factorial 3 plus z to the power 5 divided by factorial 5 and so on. Again, my sine z expansion is exactly the same expansion you all know, it is nothing but the Taylor series expansion of sine function at z equal to 0 point. So, this is both the thing, it is nothing but the Maclaurin series, it is Maclaurin series, which is the standard expression we know, it is nothing but the Maclaurin series. You should appreciate this fact. Okay. So, now we go to our next few problems where we need to find out the Taylor series expansion and corresponding Maclaurin if it is there. So, let us take another example, straightforward. If z is equal to 1 divided by 3 minus z. I need to expand this function in terms of Taylor series, but I need to know around which I am going to expand this. So, the point is z equal to 2i, z0 rather, z0 equal to 2i. And also after expanding, we need to mention about the radius of convergence of these things. I can expand, but I need to mention the radius of convergence, which we can find once I put this as a power series form. AK is known, then I can do that. So, the procedure is exactly the same that we are being using. I add 2i and subtract 2i and write this expression in this way: 3 minus 2i minus z minus 2i, then take common this, and I will have 1 minus z minus 2i divided by 3 minus 2i whole to the power of minus 1. Okay. So, now if I now expand this 1 by 3 minus 2i, then it will be 1 minus 1 plus z minus 2i divided by 3 minus 2i plus z minus 2i square divided by 3 minus 2i square, and so on. I can just expand this considering the fact this is less than 1, and that condition basically gives me the idea how the radius of convergence is there. So, in the summation form, so now I have a series. So, in the summation form, I will simply have z minus 2i whole to the power k divided by 3 minus 2i k plus 1. This is the series I have for this given function when I am expanding that series at z0 equal to 2i point. So, this is the series I have. So, it is equivalent to our old power series, as I mentioned, ak z minus z0 to the power k is equivalent to this. Now, if I compare, then we can readily find z0 is nothing but 2i and ak is this quantity. Again, I can have the value of L so AK, if I compare with that, is given as comes out to be 3 minus 2i whole to the power of k. So, a k plus 1 is 1 divided by 3 minus 2k k plus 1, and my L limit k tends to infinity a k plus 1 divided by a k is straightaway I can write 1 divided by 3 minus 2i, this quantity. So, please note that first this is the function is given and I need to expand this function around the point 2i, and if I expand it will come like this. Now, if it is this, now I need to mention about the radius of convergence, and radius of convergence is coming from this fact L value 1 by L should be my R, radius of convergence, and this quantity I need to find out. So, it will be simply mod of 3 plus 2i divided by this a plus b into a minus b, a square plus b square. So, 9 plus 4, it should be something like 13 a plus b into a minus b. So, a square it is 9 and b square it is 4. So, 9 plus 4 13. So, the result will be something like 3 square plus 4 square divided by 13 square whole to the power of half 3 square by 2 square. So, again 13. So, it will be just 1 by root over of 13. So, r which is 1 by L will be root over of 13 that. So, I find the radius of convergence here for this particular problem, and if I want to visualize that, which is important, every time I suggest you to visualize where this convergence is happening. So, it is 2i point is somewhere here. If I make a circle over that with radius root over of 13, this is the region where I can expand this function, and if you want to find out the Maclaurin series, again you just need to put 2k is equal to 2i is equal to 0, then you will have z to the power k divided by k to the power 3, k to the power 3 to the power k. So, it will be just 1 by 3 to the power k and the expansion of z. So, it will be the Maclaurin series. This, because of this 3 term, I will have this. So, the Maclaurin series can easily be figured out in this way. If I take 3 common, then it will be 1 minus z by 3 and then 1 by 3 1 by z by 3 whole to the power of minus 1. Now, the expansion gives me that this 1 by z by 3 plus z square by 3 square and so on, and the radius of convergence should be such that the value of this thing should be less than 3, because when if it is less than 3, then this quantity whatever we have is less than 1, and then this expansion is possible. So, the radius of convergence for this Taylor series is root over of 13. If I do the radius of convergence for this series, Maclaurin series, it will be something different, and it is obvious, because when I am doing the Taylor series expansion, if I put this point higher and higher, my region of convergence will be larger, and as a result I am having a radius of convergence large. On the other hand, in this case, if I do the Maclaurin series, this series will be something like this, where the radius of convergence comes out to be root over 3 or something like that. Okay. Is there any other problems? Let me check. Yeah, another interesting kind of problem. So, fz is given as z minus 1 divided by 3 minus z. We need to expand these things around some point z0 is equal to 1. This is the point where we need to expand my function. So, we will stick our old process, that means I will add 1 and subtract 1, and as a result let me find what we are getting. 3 plus 1, so I am getting like 2, and then 3 minus 1 I am getting 2, and minus say z minus 1 I am getting something like this. This is the expression I have from here. So, 3 minus z plus 1 plus 1 plus 1 minus 1. So, I am writing these things just by introducing the point I here. It is something a different kind of function that is given, 1 z is given upstairs. So, now I expand in this way. So, here z minus 1 is there, 2 is here. If I take these two common, and then it will be 1 minus z minus 1 by 2 whole to the power minus 1. The expansion will slightly change and it will be something like this. Now, I will expand this z minus 1 by 2, 1 plus z minus 1 by 2 plus z minus 1 by 2 square of that, and so on. So, the expression already I have. So, it suggests it is sum over z minus 1 k divided by 2k, k is say 1 to infinity. This expression I finally get. So, this is the series Taylor series expression of this particular function at point z0 equal to 1. So, again if I tally that with power series, then my ak comes out to be 2 to the power k. So, a k plus 1 by a k minus a k mod of that with limit k tends to infinity, which is my L, is something like 2 mod of 2 or 2. R seems to be 1 by L is half. So, that means I can expand this quantity. Sorry, one thing, because it is k is ak is 1 by 2 over k, because this is 1 over 2 by k. So, here it will be just mod of 1 by 2 and L will be 2 1 by L. It seems to be correct, because the coefficient is here in the denominator. So, A is 1 by 2 k. So, if I now try to find out what is the convergence, where it should converge, what is the region, then if it is 1, this point is 1, if I take a circle, say this point, let me put it 1 here, then if I put a circle of radius 2, then I will have something this. So, this is the region, this is the region, this is the region where this expansion is valid, and it will converge for all z's that are lying in this region. Okay. Okay, so now we will go to our next step, which is important. So, I believe you now understand how to evaluate a Taylor series at some given particular point. So, now maybe we can go to some another topic, which is called singularity and its classification. Singularity and its classification. So, singularity, we know that if a function fz fails to be analytic in some point z0, but analytic, the function fz fails to be analytic in some points z0, but analytic in some neighborhood of that point then the point z0 is called the singular point. What is the meaning of that? Fz is failed to be analytic some point z0, but analytic in some neighborhood of that point, then the point z0 is called the singular point. If we visualize these things, it will be very clear. So, suppose a function fz is given like this. So, at z equal to 0 point, the function is analytic. So, that means at z equal to 0 the function is analytic, but if I remove this 0 point, say this is a radius r, so that means mod of z less than r less than 0. So, some deleted neighborhood it is called. So, I am just delete this point 0 point, then this function is analytic in this region. In this region mod of z less than r less than 0, the function fz is analytic. However, at that particular point 0, the function is blowing up. So, that means the function should have singularity at that point. Here the singularity is at z equal to 0. Well, I can also have this kind of singularity where is the singularity? At z equal to I. So, z minus I less than some r less than 0, if I take 0 outside, this is I cut this point and take some neighborhood, I find this function is still analytic except that point here z equal to I. So, that means this point is singular point. Okay. Next thing is, now I understand what is the meaning of singular point. Next is isolated singularity. Say this is the function. Now, this function, if I write this function in this way, we have already done this in the previous class, but let me now do it more carefully. So, this function is this. So, we find that z equal to 2i and z equal to minus 2i are 2 points where the function again blows up, and these 2 points are called isolated singularity. That means, it is isolated from this point, it is isolated from other points. So, in general we call it an isolated singularity. There are many other points, I mean all these points are eventually the isolated singularity. This is an example of that. Okay. So, now again let me put something some function, say I can write this function in this way. So, how many singularities are there according to our knowledge? There is one singularity at z equal to 4, another singularity at z equal to I, and another singularity at z equal to minus I. So, there are 3 different singularity, isolated singularity are there, but is there any difference between these 2 singularities, I, these things and these things? We have something here which is called power. So, this is called the pole, this is called the pole of singularity, pole. So, by definition, say limit z tends to z0, if I multiply z minus z0 to the power n to the functions this, and if gives if it is not equal to 0 give some value, then we call, I have a singularity at z0, I multiply z minus z0 whole to the power n to the function, if it is not equal to 0 and then put limit z tends to z0, then the function fz has singularity of order n at z0 point. So, that means I have a function fz, I multiply z0 is a singularity I know, I multiply z minus z0 whole to the power n, and if it is not equal to, then I put the limit, if it is not equal to 0, then I can say this z0 at z0 point, the order of this singularity, pole of this singularity is n. If I now apply here in this particular problem, then I need to apply this limit z tends to 4, z minus 4 square fz, which is not equal to 0. When you multiply z, this term will cancel out, and then if I put z equal to 4, we have some value of this quantity. So, here z equal to 4, this is a singularity of, this is a pole of, with pole of order 2. In a similar way, limit z tends to I, z minus I fz is not equal to 0, same as this, here n value is 1. So, it is called simple pole. This is called simple pole. So, we have a singularity here of order 2, and this is order 1, this is order 1, which we call the simple pole. Okay. After that, quickly we will write 2 singularities. One is called removable singularity, which is say like sin z divided by z. If I take the, what is the meaning of removable singularity? If I take limit here z tends to 0, where is supposed, the function supposed to have a singularity z equal to 0, but if I take limit of these things, it will come to be 1. So, that means we have a singularity here at z equal to 0, but if the limit, if I put the limit here, then I will remove this singularity, that is why it is called the removable singularity. So, I can do that by expansion of z, sin z. Sin z is say z plus minus z cube by factorial 3 plus z to the power by factorial 5 and so on. Since 1 by z is here, so if I put it here, it will be 1 minus the other term. When I put the limit, this term will going to vanish and I will have 1 in my hand. So, the way we normally use the limit, I will do the same thing here, but here the only thing is that since z was originally in singularity, but when I put the limit, then I will find it is 1. That means it is removable in nature. Another kind of singularity, with that I will going to end. In the next class we will go more about singularity. Today we do not have much time. It is called essential singularity. Essential singularity is the singularity which we can't remove. For example, the expression e to the power 1 by z, the function something like this. At z equal to 0 point, this function has essential singularity. So, the singularity is there, you can't remove anyway. So, if I expand this function, it will be just 1 plus 1 by z plus 1 by z square 1 by factorial 2, 1 by z cube 1 by factorial 3 and so on. Now, if I put the limit z equal to 0, at z equal to 0, this power of z is going up. So, you never have a process to remove this singularity. That is why it is called the essential singularity. So, today we have learned. So, let me conclude this class here. Today we have learned initially how the Taylor series can be expanded, and next we learn very briefly about the singularity. In the next class again we will recap all these singularities and gives you more examples of different kind of singularities, which is important. But in the next class we will start something related to series, which is called the Laurent series. So far we learned how to expand an analytical function in a region where it is analytic, but if the region is bounded by something, say some annular region is there, if I want to expand that function for that annular region, how to expand this function is basically given by this Laurent series, and from that we will have important few important outcomes like the residue and all these things. So, with that note, let me conclude the class here. In the next class we start with the singularity and try to find out what is the meaning of Laurent series and how to expand a function in a boundary or in some annular region. So, thank you for your attention. So, see you in the next class. Have a good day.